Okay, now going back to page 46 of your preliminary calculus booklet, we're going to look at something called differentiation by first principles. Now, this is very similar to the limits that we were doing earlier on when we were doing the gradient of the secant PQ. So when we were doing gradient of secant PQ previously, we were calling this point A function of A, that's what we were calling point P, and we were calling point Q x function of x. But now we're going to rename these points and call them something else. So when we do what's called differentiation by first principles, the reason it's called differentiation, it allows you to find the gradient of the tangent at the point P. Now it's called differentiation because we end up obtaining another function which is actually derived from the original function. Now, when we get the gradient of the tangent at P, that function that we end up with is actually called the gradient function. And the way that we write the gradient function, if we've got the normal function is y equals fx, then the gradient function is y equals f dashed x. That's the notation that allows us to know that it's the gradient function. So it's y equals f with a little dash there, x, okay? And that gives us the gradient of the tangent at point P. Now, we're going to use limits again, and instead of calling this A, we're going to call this x. Therefore, point P will be x across, and because the curve, you substitute the x value into the curve, it will be the point x comma function of x, okay? So point P is now going to be called x function of x. I'll just write that here. So x comma function of x. Now point Q is not going to be called what it was called before. If this is x here and this extra little bit here is h, then this point here will be x plus h. So Q will have coordinates x plus h. And then we substitute the x plus h value into the function, and the y value will be function of x plus h. Okay, so we'll just fill that in here. P has coordinates x function of x, and Q will have coordinates x plus h comma function of whatever x plus h is. Okay, so we go x plus h across. The y value here will be function of x plus h. So x plus h, function of x plus h up. Okay. Now, when we do the gradient of the tangent, remember it's always y2 minus y1 over x2 minus x1. And y2 is function of x plus h, and y1 is function of x. So the gradient of PQ, this is of the secant PQ. So the gradient of secant PQ is y2, which is function of x plus h, minus y1, which is function of x, over x2 minus x1 is x plus h minus h. Now, remember, we don't want the gradient of PQ, we want the gradient of the tangent. So as Q gets closer and closer to P, then this h will get smaller and smaller, and h will approach 0. So as Q approaches P, the gradient of the secant PQ approaches the gradient of the tangent at P. That is, as h approaches 0, as h gets smaller and smaller and approaches 0, the gradient of the secant will approach the gradient of the tangent at P. So now we can do this gradient again here with the limit formula, with the limit bit as well. And so using limit notation, we write that the limit as h approaches 0 of the gradient of the secant will equal the gradient of the tangent at P. And so therefore the gradient of the tangent at P will be the limit as h approaches 0 of, this is y2 minus y1 over x2 minus x1, which is function of x plus h minus function of x, over x2 minus x1, which is x plus h minus h. Notice that x plus h minus h will actually equal x, okay? However, since the point P, which is x function of x, is a general point on the curve, okay, like up here, P is just a general point on the curve, it means that the limit as h approaches 0 of function of x plus h minus function of x over x plus h minus h is a function. In fact, it's what we call the gradient function. And if you could please put this into a box. So therefore, this is how we find the gradient function f dashed x. It's the limit as h approaches 0 of function of x plus h minus function of x over h. Okay, so you need to learn that. Okay, please turn to page 48. There's a blank page on page 47. We're going to look at these examples. So we have to differentiate function of x equals x squared plus 3 from first principles. When we're being asked to differentiate it, what it's asking us to do is to find the gradient function. So we're trying to find f dashed x. Now it's all worked out here, but I'm going to do it over here as well. So the gradient function is the limit as h approaches 0 of the function of x plus h minus the function of x over h. Now what I normally do, yes, we write that out, but I normally work out I write down what function of x is first, and it's x squared plus 3, and then I work out what function of x plus h is. So we've just got the formula there, okay? So before I substitute into that formula, I will write down what function of x is, which is x squared plus 3, because it's given to you up here. Then write down what function of x plus h is. Now, function of x plus h means we just substitute any x values with x plus h. So this x value gets substituted with x plus h. So the function of x plus h means replace the x here with x plus h. We've replaced it there, so it's x plus h squared plus 3. Then we expand this, so we get x squared plus 2xh plus h squared plus 3. So therefore, this is the function of x plus h. Now we can substitute into the formula. So f dashed x is, make sure you write it out completely, the limit as h approaches 0 of the function of x plus h. Now I've got that up here, so I'm just going to substitute in now. So it's x squared plus 2xh plus h squared plus 3. Now that's the function of x plus h. Minus, now the function of x is x squared plus 3. So it's function of x plus h minus function of x over h. So simplifying the numerator, we get x squared, this will be minus x squared. So the x squareds will cancel. And so the x squareds go and we get 2xh plus h squared. Now we've got plus 3 minus 3, that goes as well. Okay, over h. Now we can see that h is a common factor here in the numerator. So we can factorize it out and cancel the h's. And we get that it's the limit as h approaches 0 of 2x plus h, and now we substitute h is 0 and we'll end up with 2x plus 0, which is 2x, okay? So this is how we do it. You may want to take an extra row here where you open your bracket up here and expand before going to this step here, okay? Now, we're going to do question 2. Now we're differentiating y equals x squared plus 5x from first principles. And function of x plus h will replace any x's in this function here with x plus h. So this x gets replaced with x plus h. So we get x plus h squared plus 5 times this x here gets also replaced with x plus h. And now we need to expand that. So we get x squared plus 2xh plus h squared plus 5x plus 5h. And then we collect any like terms if we've got any. And I don't think we do. So that's what we've got there for our function of x plus h. Therefore, f dashed x, which is the gradient function, is the limit as h approaches 0 of function of x plus h minus function of x over h. Now we can substitute it in. So it's the limit as h approaches 0 of x squared plus 2xh plus h squared plus 5x plus 5h. Now that is the function of x plus h. Then we go minus, then we need to subtract x squared plus 5x. So I'm going to go minus x squared minus 5x because I'm really putting a negative in front of all of this. So it's minus x squared minus 5x. Okay, do not put you either put minus bracket x squared plus 5x and then open the brackets on the next row, or you go minus all of this. So minus x squared minus 5x straight away over h. let's simplify that by collecting any like terms. Now the x squared terms cancel, and the 5x and the 5x cancel. So we've got 2xh plus h squared plus 5h, because we lose the x squareds and we lose the 5x's. So we've got 2xh plus h squared plus 5h over h. Remembering to write limit as h approaches 0, because we keep writing that limit as h approaches 0 until we do our substitution. We still cannot substitute. So it's the limit as h approaches 0. And we can see that h is a common factor in the numerator, so pulling that out and cancelling the h's, replacing them with 1's, we get the limit as h approaches 0 of 2x plus h plus 5. Now we can substitute in h is 0, and if we do that we get 2x plus 0 plus 5, which is 2x plus 5. So therefore, I'll just put it down here. So therefore the gradient function f dashed x is 2x plus 5. Okay? We'll now go to question 3. Actually, I'll go up to question 4 first. So we're differentiating function of x equals x to the negative 1, x to the power of minus 1 from first principles. So let's just write down what function of x is and function of x plus h is. So function of x is x to the power of negative 1, which really is, writing that in a simplified format, that is 1 over x. Okay? Function of x plus h. Function of x plus h is replacing the x here with x plus h. So it's 1 over x plus h. Therefore, the gradient function f dashed x is the limit as h approaches 0 of the function of x plus h minus, this is a minus, so minus the function of x over h. So we get, let's substitute in what function of x plus h is. So it's the limit as h approaches 0. Function of x plus h is 1 over x plus h minus function of x is 1 over x, and then we go over h. So again, it's the limit as h approaches 0 of all of this. Now, we cannot substitute h is 0 in here, otherwise we'll get an undefined function. So what we need to do, let's make a common denominator here on the numerator. So we'll get x minus... So we're multiplying this first fraction by x over x, and we're multiplying this second fraction by x plus h over x plus h. So we get x minus bracket x plus h over x times x plus h, and that's all being divided by h. Okay, now we're going to need 2 columns here. So it's the limit as h approaches 0 of x minus h if we expand that. So we get x minus h over x bracket x plus h. Now I'm going to put this over h over here. So I'm going divided by h. Okay? So instead of going fraction over fraction, I'm doing this fraction going divided by h. So it's the limit as h approaches 0. Now x minus h is negative h over x bracket x plus h. Now remember, we're dividing by h, which is the same as multiplying by 1 over h. Okay, so dividing by h here is dividing by h over 1. That's the same as multiplying by 1 over h. Notice our h's will cancel, and in their place we can put 1's. So it's the limit as h approaches 0 of negative 1 over x bracket x plus h. Now we can substitute in our h is 0, remembering to put equal signs here, and we get that that is equal to 1 over x bracket x plus 0, which is negative 1 over x times x, which is negative 1 over x squared. Okay, and that is differentiating x to the power of negative 1 from first principles. Question 3, differentiate function of x equals root x from first principles, actually is a little bit of a tricky one. And when you try and use this method, that the gradient function equals the limit as h approaches 0 of function of x plus h minus function of x over h, you end up with a dead end, and you can't go any further. So here our function of x is root x, and our function of x plus h means to replace any x's here with x plus h, and we get square root of x plus h. Then writing our gradient function, which is the limit as h approaches 0 of all of this, we get limit as h approaches 0 of function of x plus h is root x plus h minus function of x is root x over h. Now we find that we cannot simplify this. So to use this method, it's actually quite difficult to use this method. So I never use this method for differentiating root x. What I do is, if we go back thinking about how we were originally doing the questions, where when we're working out the gradient of the tangent, where we've got 2 points and our points are a and x. So for example, where you've got your curve and you've got your point here, a, function of a, for example, and you've got your point here, if you want the gradient of the tangent there, and you've got your point here, x, or you can even call it c if you want, function of c, okay? The gradient of the secant is function of c minus function of a over, we'll call this c, okay, over c minus a, because it's y2 minus y1 over x2 minus x1. So instead of doing the question like this, we can also do it like this, that the function of x is the limit as h approaches, not h approaches 0, it's the limit as c, approaches a of, and here's my gradient, function of c minus function of a over c minus a. So it's as c gets closer and closer to a, that and the gradient of the secant, remember, is y2 minus y1 over x2 minus x1, which is function of c minus function of a over c minus a. Now I'm calling it c, function of c, because I've got x's up here and I don't want to use the same pronumerals, okay? So when you're differentiating something with the square root, do not use this version, function f dash x is the limit as h approaches 0 of this function, because what happens here is that you cannot simplify the numerator. So what we do is we use this version of differentiating from first principles. Now it's exactly the same thing, just using different pronumerals. Rather than h approaching 0, we get c, the x value here approaching this x value there, because we want the tangent, let's say, at the point a here. So it's the limit as c approaches a. Now function of c means to just replace the x here with a c. So it's root c, minus function of a means to replace the x here with an a over c minus a. Now we did something like this earlier. Now what we can see is that the denominator can be written in terms of square roots, and it can be written as root c squared minus root a squared. Now this is now written as a difference of 2 squares, so it's the limit as c approaches a of root c minus root a. Now this is a squared minus b squared, which is a plus b, a minus b. So therefore our root c minus a's will cancel, and therefore it's the limit as c approaches a of 1 over the square root of c plus the square root of a. Now we can substitute in, so we're replacing our c with an a, so it's 1 over the square root of a plus the square root of a, which is 1 over 2 root a. Okay, now actually looking back at the question, sorry, I should have called this x function of x. Okay, so what I want to do is replace all the a's and the function of a's with x function of x. So I'm going to go that this is x, so all the a's, replace them with x's, okay? Or I can just do it at the very end, but I probably should have done it at the first bit, because we are differentiating at this point here. So all the a's are x function of a. So I'm just replacing all the a's with, x's. And if I do that, replace all the a's with x's, I get 1 over 2 root x, okay? So sorry about that. Call this x function of x, call this c function of c, or any other pronumeral that you want, okay? And it'll be the limit as this value c approaches this value x, okay? Function of c minus function of x over c minus x. And you will end up with 1 over 2 root x. Now, if p is the point of tangency here at this point, so P is the point of tangency and P is a fixed point on the curve. Again, PQ is the secant of the curve, and we've got y equals function of x. Where Q is a point that is near P, we can say that the gradient of secant PQ is, if we want the gradient of sec, this is another different set of notation again for limit function. So if we want the gradient of PQ, it's the change in y values over the change in x values. So it's rise over run. Now, if we're saying that these values are very small, remember change in means delta y, and change in x values means delta x. You may have seen that in science. So gradient is rise over 1, which is the change in y values over the change in the x values. So the gradient of secant PQ is the change in y values over the change in the x values. Now, as Q approaches P, the gradient of the secant PQ approaches the gradient of the tangent at P. In other words, as x, well, this delta x. So this delta x, as that approaches 0 and gets smaller and smaller, then the gradient, which is delta y over delta x, will approach the gradient of the tangent. We can write this using limit notation, as shown below here. So it's the limit as delta x approaches 0. So as Q gets closer to P, delta x will get smaller and smaller and approach 0. So the limit as delta x approaches 0 of delta y over delta x is the way we can write the gradient of the tangent at P. Now, instead of writing limit as delta x approaches 0 of delta y over delta x, it's actually abbreviated as the following, dy dx, okay, where dy dx is the derivative. So when you're working out the gradient function, you know how we've got y equals function of x, and before I was just telling you that that's the normal function and that the gradient function is f dashed x. Well, if your original function is y, that's your original function, your gradient function, so these are the gradient functions. So the gradient function, this is the original function, y is fx. So your original function would be y equals fx, and then the gradient function would be f dashed x. Or if your original function is y equals something, then to write the derivative function, we write dy dx, okay? So dy dx is the gradient function. It's the abbreviated version of this whole gradient function here. So the derivative, dy dx, is not a fraction, but it's the limit of the fraction delta y over delta x, okay? So it's just some notation that you're going to see later, okay? So just writing it all down again. Actually, no, I won't write it all down again. I'll discuss it in class with you, and I'll just set some homework now. What I'll do down here is to find the gradient function, just a little summary. To find the gradient function, we either use, so we've got f dashed x equals the limit as h approaches 0 of function of x plus h minus function of x over h, or we can use that the gradient function f dashed x is the limit of function of x minus function of a over x minus a, so it's the limit as a approaches x. And I'll just draw that for you, where you've got a curve and you've got the point x here and you've got the point a there. Yes, it's the limit as a approaches x, okay, of function of x. Sorry, actually it's the other way around. It's the limit as x approaches a. Sorry, one sec. It all out. I'll just draw it again, and we'll do it like we did the last example, where we've got, if we want the point of tangency here at x, and we'll call this other one point C, for example. So f dashed x is the limit as, remember, c has to get closer and closer to x, so it's the limit as c approaches x. Remember, we've got the point here x function of x, and here we've got the point c function of c, so the gradient will be function of c minus function of x over c minus x, okay? So the only time you would use this second version of the gradient function, so f dash x is the limit as c approaches x of function of c minus function of x over c minus x, is if you were differentiating something from first principles. If you were differentiating something like square root of x function. So if you're differentiating a function that's a little bit more tricky, like differentiating square root of x from first principles only, you would use this version of the function, okay? or if you're trying to use this version and you get stuck, okay, where you can't do any factorising like we couldn't do in example 3 on the previous page, you would then resort to using this method, okay? Now for homework, I want you to go to your textbook and just look at exercise 8.4. Now, if you look at that, the introduction to that, that's the theory that we just did. We didn't do it, so we looked at this version here of function of, well, they did f-c, but I was doing f-x. Notice it's that same formula, that second formula that we were looking at. Then we looked at this f-x, if you can see the box on the screen, is limit as h approaches 0 of function of x plus h minus function of x over h. So when you differentiate from first principles, this one here, is the version I do want you to use. You would only go back and use this other version up here if you were stuck, okay? If you couldn't use that first version, this other version down here, okay? And this is what I just briefly spoke about a minute ago using dy dx notation, but we're not going to do any questions really like that at the moment. I want you then to go to the method that we're really going to use is method 2, but we're not substituting in any values yet. So we're just going to be looking at, if you look at this example here, differentiating this from first principles, such as on page 463, this example here. That's what we're going to be doing in this exercise, only questions like that, okay? There are other types of questions, but we're not doing them yet. So in exercise 8.4, I just want you to do question 12 only. So exercise 8.4, all of question 12. So exercise 8.4, question 12 all. Please do not do any other questions from this exercise. So I just want you differentiating from first principles using this method up here. Okay? Thank you.